Welcome to the next video, which is continuation part of the mathematical modeling or of an electrical system in transfer function model. Okay, so as in the last video we discussed about the V equal to IR, V equal to LdI by dt, and V equal to CdU by dt. That sorry, I equal to CdU by dt that we discussed, right? So the continuation part is that one. So transfer function model of a electrical system. Topics to be covered is the same using transfer function. So this is the same block diagram what we discussed in the yesterday's class. So that's sorry before video. So the example what I'm changing here is I'm changing a little bit of terminologies here to understand as a which is input and which is output. So that's right. So V in as Vs, whatever this Vs is there, that Vs I am changing is as a V in of t, and the whatever the output is there, that I'm considering it as a V out, because with respect to whenever we need to have both the output and the input, then only we can get the transfer function. Transfer function is a combination of the both inputs and outputs. Okay, so that means V out will be here. Okay, V out will be across the total series function. I'm considering like this. Okay, because there is no other sources of this, so I'm considering that one. So V out of t and V in of t, input voltage. So using KVL, by using KVL, as we already know Kirchhoff's voltage law, so V in of t, that means V in of t equals to, it is distributing to all these three elements, so that equal to, with respect to I and R. So as we need to, as a Kirchhoff law, we need to write with respect to I, all voltage based terminals. So that's why R and I. Okay, V equal to I here, so that one, and also V equal to LdI by dt, and 1 by C integral of I dt. Okay, so in this way we are writing. So now, but when you need to transfer function, the terminology is not to be in the time domain. Okay, it needs to be converted into the S domain analysis. So regarding that one, what we need to do is we need to consider in Laplace domain. That means regarding that one, we need to apply the Laplace transfer function. So this one. So when we are applying Laplace transform, then automatically this time domain will be converted into V in of S and plus R I of t. Here I of t, I of t, I of t will be that I am consider I'm getting a complete one common point r into I of s. Yes, this di by dt will be considered before solving the next further equations and everything. So you need to understand the conversion ratio of the differential equations to the Laplace transform, differential equations to the integrations, integral equations to the Laplace, and everything, because these are most common things which we'll be placing in the next coming equations and coming video lectures. Okay, so r of r into I of s, L into di by dt will be written as s into I of s, and integral of I of dt is written as sc. Okay, s of I of s. Okay, that we'll consider in the coming this way. And after that, the output voltage is considered is across the capacitor. Then automatically what will happen is V out of s is equal to 1 by sc I of s. I'm considering, sorry, before I wrote it like this, this also you can write it, then automatically what will happen is V in and V out will be the same. That means totally the output will be the the transfer function will be equal to 1. But when it comes to the V out, if I'm considering only this side, then automatically what will happen is the remaining these two also will be become as a input functions. Then automatically the transfer function will be related to the V out of s by Vn of s is equals to 1 by sc by r plus sl plus 1 by sc. Okay, this is the how the normal in general the RLC circuit will be written in the in terminologies of transfer function. Now I am taking another example. So the simplified equation is that one. Another example is the very famous one, that is low pass RC filter. Low pass RC filter means a resistor which will be connected to the capacitor in parallel. So input voltage will be across the R and both output voltage across the capacitor. So regarding this, we need to write the transfer function. For an RC low pass filter, what we need to do is the same output voltage, the same how the it will come, the same as before. Just now I explained that one. In the same way, if you do that one, so you will get the output voltage equation. That means transfer function as V out of s by V in of s equal to 1 by RCS by RCS plus 1. Okay, this way we can able to write. This shows the how frequency response changes the RCN domain, because here S will be impacts the frequency, because the C and how it will be impact on the resistance and everything that we can see with respect to that one. These models are the functional models of for the control system design in the power electronics, audio filters, communication analysis, communication circuits, many places. This RC low pass filter will be the very famous and very important one when you are studying about the control system. That one. Okay, we need to demand. The next one is important things what always you need to design when you are designing a transfer function is always you remember the initial conditions will be always zero. Otherwise, if the people are saying like that, there are some initial conditions will be there when you are writing any mathematical solving problems with, then automatically if that having a initial condition, then they will give the initial condition. This is the initial condition. So then only you need to consider that initial condition. Otherwise, the initial conditions always will be the zero only. Okay, and the next one is use Laplace transform for easy understanding and reducing the total equation, bigger equation into the smaller equation. So that will help you to reduce the equation format. And the next one is check units and dimensions consistently. And the system analysis, that means mechanical to electrical, electrical to mechanical, rotational to mechanical, rotational to electrical. These things will be very important when you're writing the transfer function equation. Okay, thank you.